Think about how incredible it would be for robots to truly learn by doing in the real world.
Yeah.
Not needing someone to write a million lines of code or reward every single tiny step.
Yeah, it's a huge challenge.
Especially when you consider the sheer messiness, the unpredictability of everyday environments. It feels like a monumental task.
It really is. How do you get an AI to just explore and make sense of things, interact with a world that's constantly throwing curveballs, all without like explicit instructions?
Exactly. And that's precisely what we're diving into today. We've got this fascinating research paper, Imagine, Verify, Execute, Memory-Guided Agentic Exploration with Vision Language Models.
From Lee and colleagues, 2025. Looks really interesting.
Yeah. So our goal here in this deep dive is to really get a handle on how this work offers a brand new way for robots to explore independently, making them more autonomous learners in those complex real-world settings.
And we know you want to get the crucial info efficiently, thoroughly, without getting too bogged down in the weeds.
Right. So let's jump right in. This research, it tackles a core issue in robotics, doesn't it? The limits of traditional reinforcement learning, or RL.
It really does. RL has shown some, impressive results in simulations, controlled environments.
But it often hits a wall in the real world.
Exactly. The sheer complexity, the open-ended nature, it struggles. There's this big gap between what a robot theoretically knows or learns in simulation and what it can actually do effectively, physically, in our world.
Okay, and this is where vision language models, VLMs, come in. These AI systems that can understand what a robot sees and what we tell it.
Yeah, they seem like a perfect fit on the surface.
But the paper points out they have their own struggles, right? Like grounding their understanding the physical world.
Yeah.
And memory.
That's a key point. They struggle with that physical grounding and also with remembering past experiences in a way that's, well, genuinely helpful for future actions.
Okay, so this IVE framework they're proposing, Imagine, Verify, Execute. What's the core idea there?
Right, IVE. It's a new system for agentic exploration. And what's really cool is how it draws inspiration from, well, us. Humans.
How we explore.
Yeah, think about it. We're driven by curiosity, right? A desire to discover new things, figure out how our environment works. Figure 1A in the paper actually illustrates this human drive, seeking novelty, learning.
Which is pretty different from how traditional RL often works. Figure 1B shows that RL stuff often relies on, what, intrinsic rewards.
Right, like little digital breadcrumbs to encourage novelty, or just sampling goals randomly.
Which sounds a bit haphazard, especially for the real world. Maybe even dangerous.
It can be very inefficient, yes, and potentially hazardous. IVE, shown in Figure 1C, offers a much more structured approach. It uses these VLMs in a loop.
A loop?
Yeah, a tight loop.
Yeah.
Imagine potential future scenarios, verify if they're physically plausible, and then execute actions to try and make them happen.
This is like giving the robot a more focused, maybe structured kind of curiosity.
That's a good way to put it. And the paper emphasizes its modularity. It's built from different pieces working together.
Okay, what are the key components then? You mentioned modularity.
So the main ones are the scene describer, the explorer, the verifier, and a memory module. And these all connect to what they call action tools.
Let's start with the scene describer. What's its job?
The scene describer is basically how the robot makes sense of what it sees. It takes the raw visual input, the RGB images, color, and depth, and uses a VLM to turn that into something called semantic scene graphs.
Semantic scene graphs. Okay, let's unpack that a bit. What does that actually mean for the robot? Like practically?
Okay, imagine you've got, say, a red cup, a blue block, and a tray on a table. The scene describer doesn't just see pixels.
Right.
It identifies red cup, blue block, tray as distinct objects. And crucially, it understands how they relate to each other spatially.
So the relationships too.
Exactly. Equations 1 and 2 in the paper show this. The nodes in the graph are the objects, and the edges describe relationships like blue block stacked on, tray, or maybe red cup near tray.
So it's abstracting the messy visual stuff into a simpler, almost language-like map with labels and connections.
Precisely. It simplifies the reasoning process for the robot enormously.
Okay, so this simplified scene understanding, this graph, it feeds into the Explorer module. What does that do?
Right. The Explorer takes that current scene graph, looks back at past experiences stored in the memory module.
We'll get to memory in a sec.
Yeah, and using this current scene and past memory, it tries to imagine potential future scene graphs, new arrangements, new relationships between the objects.
So it's dreaming up possibilities.
Kind of, yeah. And it also generates sequences of high-level skills needed to achieve those imagined scenes. Things from a predefined list like move the cup to the left of the tray. Equation 3 gives an example of this.
And how does it make sure these imagined scenes are actually new?
Good question. It compares the imagined scenes to the ones stored in its memory from past explorations. It's actively trying to generate novel transitions, changes it hasn't seen or created before.
That's the curiosity part kicking in again. Seeking novelty.
Exactly. It's a key part of the human-inspired drive, aiming for new, interesting configurations.
Okay, explore dreams up possibilities. But, just because you can imagine stacking 10 blocks doesn't mean you can do it. How does the robot know if these ideas are actually feasible? That's the verifier.
That's exactly the verifier's job. It's the reality check.
Okay.
It assesses the physical plausibility and the stability of the skill sequences that the explorer proposes. And importantly, it uses the robot's recent interaction history to make better judgments.
So it's not just the VLM thinking it might work, but checking against actual recent physical experience.
Precisely. Did something similar fail recently? Was it unstable? The verifier learns from that.
And what kind of feedback does it give? Just yes, no?
It's pretty straightforward. Yes, go ahead, or no, don't. But if it's no, it also provides reasons.
Oh, like why it won't work.
Yeah. Like, is it infeasible? Maybe the robot physically can't reach or manipulate like that. Is it unstable, likely to fall over? Or did the plan just deviate too much from the original imagined goal? Equation 4 has an example, like trying to stack a cup on an already full tray.
The verifier would flag that as unstable. Makes sense.
Right. Am I saying no, unstable, or maybe even suggest a prerequisite like clear the tray first?
That's really clever. So it's considering the robot's own body, the environment's physics, embodiment constraints, environmental dynamics, stability, potential occlusions, clutter, all of that. It's grounding the imagination in physical reality.
Okay, now let's circle back to the memory module you mentioned. What's its specific role?
So the memory module stores the robot's history. All those past scene graphs it's generated and experienced, they're stored as compact symbolic summaries. The paper mentions using the Network X library for this graph stuff.
And the Explorer and Verifier use this memory. Yeah, they query it, they look for similar past experiences. The similarity is measured using something called an edit-based graph distance. Equation 5 talks about this with a threshold.
Edit-based graph distance. Okay, simpler terms. How does that work conceptually?
Think of it like comparing two structures built from Lego bricks. The edit distance is basically the minimum number of bricks you'd need to add, remove, or change the position of to make one structure identical to the other.
Okay. So the robot asks its memory, have I seen a scene kind of like this before, with the cup and tray arranged similarly?
Exactly that. What happened last time I tried something like this?
And this memory serves two purposes then.
Right, a dual role. First, it helps the explorer aim for novelty. What arrangements haven't I seen? Second, it gives the verifier crucial context for its feasibility checks. Did a similar setup work or fail before?
Okay, so we have imagining, verifying against memory and physics. What's the final step? Getting the robot to actually do something. Action tools.
You got it. The Action Tools module takes those high-level skills from the explorer like move cup left of tray and translates them into the low-level commands the robot's motors understand. The actual arm movements, the trajectories. Figure 4 shows this process.
And these tools are categorized.
Yeah, they break them down into 3 types. First, relation-based placement tools. These handle placing objects relative to other objects using those semantic labels like stacked on to the left of.
Like putting the cup on the tray.
Exactly.
Yeah.
Second, region-based placement tools. These place objects into predefined general areas like specific grid cells in the workspace. Figure 9 in the appendix mentioned this. Think putting recycling into the bin.
Sorry.
And third, there's an arranger tool. This one's for decluttering moving objects out of the way to clear space, tidying up.
That arranger tool sounds super useful for real-world messiness.
Definitely. And the key here is modularity again. You could potentially add more complex tools later.
So that's the whole IVE system. How did it actually perform? Did it work?
They tested it thoroughly, both in simulation using VimaBench and with a real UR5E robot arm on a tabletop.
And the results.
Pretty impressive. The main finding was that IVE significantly outperformed the traditional RL baselines like R&D and RE3 when it came to exploration diversity.
Diversity meaning It found more different states.
Exactly. They measured it using state entropy. IVE showed a 4.1 to 7.8 times increase compared to the RL methods.
Wow, that's a big jump.
It is. And maybe even more strikingly, IVE achieved between 82% and 122% of the scene diversity that expert human explorers achieved in the same setup. That's shown in Figure 6.
So comparable to humans, sometimes even better. How? And why did the RL methods fall so short?
Well, the paper suggests RL often gets stuck chasing pixel-level novelty. Like, just seeing a slightly different view might count as novel, even if the objects haven't really interacted in a new, meaningful way.
IVE focuses on the semantic novelty, the relationships.
Right. And IVE's memory helps it scale better than humans, too. We might forget some configurations we've already tried, but IVE remembers, helping it push towards truly new states more consistently.
That makes sense. Did it matter which VLM they used?
They tested that too. Figure 7 shows it's pretty robust. It performed well across different VLMs, not just one specific model.
And they did those tests where they removed parts of IVE, right? The ablation study? What did that show?
Yeah, Figure 8. That was really revealing. Removing the memory module or the Explorer caused the biggest performance drops.
So imagination and memory are critical.
Absolutely. Huge drop in the number of unique scenes discovered. Removing the verifier also hurt performance, leading to more failed or unstable attempts.
So all the parts really do matter. It wasn't just about exploring either, right? The data IVE collected was useful.
Hugely useful. That's another key finding. They used the data IVE gathered autonomously to train other things, like policies for specific tasks using behavior cloning, and also Training World models the robot's internal physics simulation.
And how did that compare to using, say, human demonstration data?
Tables 1 and 2 and figures 10 and 11 show this. Policies trained on IVE's data performed comparably, sometimes even better than policies trained on human data.
Really? Better?
Yeah. And the world models trained on IVE data were also very accurate. It suggests this kind of autonomous, curiosity-driven exploration generates really high-quality, diverse data that's great for downstream learning.
So it's not just exploring for exploring's sake. It's generating useful training material automatically.
Exactly, which gets us closer to that idea of more general-purpose robots that can learn lots of skills without needing humans to show them every single thing.
Okay, so let's quickly summarize the main contributions for everyone listening.
Sure. I'd say it's really 3 things. 1, the IVE framework itself, this cool idea of curiosity through imagining and verifying. 2, showing you can collect rich robotic data without needing rewards, just using VLMs in this structure. And 3, proving it works in simulation and the real world, boosting exploration and helping downstream tasks.
Of course, no research is perfect.
Yeah.
What did the paper identify as current limitations?
Well, there's latency. VLMs can be slow to reason, which slows down the whole loop. The action tools are currently hand-defined, which might limit scaling to totally new types of actions.
Right, you'd need to program new tools.
And it relies on good object detection. If it can't see or identify an object correctly, especially if it's hidden or totally novel, the system might struggle.
Makes sense. And what about future directions? Where could this go?
They suggest a few things. Using faster, lighter VLMs could help with the speed issue.
Okay.
Integrating learned policies as action tools so the robot learns new basic skills itself. That would be a big step towards more adaptability.
Definitely.
And also improving perception, maybe using multiple camera views or allowing the robot to physically interact to uncover hidden objects, that sort of thing.
So IVE really feels like a significant step, enabling robots to learn and explore more like us in these complex spaces.
It's fascinating how that human inspiration, curiosity, imagination, checking against reality leads to a more effective, more grounded approach than just rewarding novelty directly.
And the value of the data it collects for learning other skills. That really seems key for making robots more generally capable, doesn't it? For you listening, this move away from constant human supervision is a really big deal in AI and robotics.
It truly is. And it leaves us with a pretty big thought to chew on, doesn't it? Think about the implications if robots can autonomously explore and learn like this. Imagine disaster response robots adapting on the fly, or assistive robots learning the specifics of your home without needing explicit programming for every corner.
How does it change how we interact with robots? How we use them?
Yeah, what entirely new capabilities might pop up when these systems become genuinely curious and adaptable to the sheer complexity of our world? Something to think about.
Definitely some thought-provoking questions. If you want to get into all the nitty-gritty details, we absolutely recommend checking out the full paper by Lee et al. It's got all the experimental data and methodology. Thanks for joining us for this deep dive.